Welcome to the Midnight Lesson. Tonight we're stepping into Yellowstone National Park, a place where forests, rivers, and wildlife sit on top of one of the most powerful volcanic systems on Earth. In this lecture-style episode, we'll explore the Yellowstone supervolcano, the caldera beneath the park, and the hydrothermal engine that drives its geysers and hot springs, while also visiting the animals that live on this volcanic ground, from bison to canis lupus. If you have ideas for future topics you'd like to fall asleep to, leave them in the comments. Now settle in, get comfortable, and enjoy tonight's midnight lesson on Yellowstone. Yellowstone, not simply as a national park or a tourist destination, but as a living geological system. When people think of Yellowstone, they often picture geysers, bison, and dramatic landscapes. Those are certainly part of the story, but what we are really looking at is one of the most complex volcanic and hydrothermal environments on Earth. Yellowstone is, in a sense, a window into deep planetary processes that normally remain hidden beneath kilometers of rock. Yellowstone National Park spans parts of 3 U.S. states, primarily Wyoming, with sections extending into Montana and Idaho. The park covers roughly 2.2 million acres, and within that space we see a concentration of volcanic, tectonic, and biological activity that is unmatched anywhere else on the continent. From a geological perspective, Yellowstone sits on top of a mantle hotspot, and that hotspot has shaped the region for millions of years. It is the engine that fuels the famous hydrothermal features, and it is the reason Yellowstone is often described in popular media as a supervolcano. Before we go further, we should clarify what that term means. Supervolcano is not a formal scientific category in the way that stratovolcano or shield volcano is. It is a media-driven term that generally refers to volcanoes capable of producing eruptions exceeding 1,000 cubic kilometers of erupted material. Yellowstone qualifies because its past eruptions include events of that magnitude. However, the term can also distort the real science, because it encourages people to imagine Yellowstone as a single, giant mountain that might explode at any moment. Yellowstone is not a cone-shaped volcano. It is a volcanic field with a large caldera system, fed by magma bodies that interact with groundwater and crustal rock. The caldera is one of the key geographic features we'll focus on today. A caldera forms when a large volume of magma is erupted, and the ground collapses into the emptied space below. Yellowstone's present-day caldera is roughly 45 by 30 miles in size, stretching across the central portion of the park. It is not always obvious to visitors because the landscape is not a dramatic crater in the way many people expect. Instead, it appears as a broad basin surrounded by high terrain. Locations like the Yellowstone Lake area and the Upper Geyser Basin exist within this larger caldera structure, and their behavior is connected to it. The hotspot beneath Yellowstone is part of a longer geologic track. If we follow the path of volcanic activity backward in time, we can trace a line across southern Idaho and into Oregon and Nevada. This track reflects the movement of the North American plate over a relatively stationary mantle plume. The result is a chain of calderas and volcanic deposits that mark where the hotspot used to be. Yellowstone represents the current position of that hotspot beneath the continent. So when we talk about Yellowstone, we are not just talking about a park. We are talking about the surface expression of a deep earth process that has been active for at least 16 million years. Now, Yellowstone is not only geology. It is also ecology, and the biological systems here are tightly linked to the physical environment. The animals that Yellowstone is famous for live in habitats shaped by volcanism, glaciation, and hydrothermal chemistry. One of the most iconic species is the American bison. Bison. These animals are often seen in the Hayden Valley and Lamar Valley, grazing in open grasslands and moving in herds that can number in the hundreds. Their presence is not incidental. The valleys they occupy are shaped by volcanic deposits and sedimentation, creating nutrient-rich soils that support grasses and sedges. Another species frequently associated with Yellowstone is the gray wolf, Canis lupus. Wolves were reintroduced to the park in the 1990s, and their ecological role has been widely discussed in terms of trophic cascades and predator-prey dynamics. Wolves primarily hunt elk, Cervus canadensis, which are abundant in the park and migrate seasonally. The interaction between wolves and elk influences vegetation patterns, especially along riparian corridors, where browsing pressure can affect willows and aspens. While today's lecture is focused on volcanism, it is important to recognize that the landscape and the biology are inseparable in a place like Yellowstone. We should also mention the grizzly bear, Ursus arctos horribilis, and the American black bear, Ursus americanus. Both species occupy large territories in and around the park, and their survival depends on a mix of food sources including roots, berries, insects, and occasionally carrion. In the context of Yellowstone's geothermal areas, it's worth noting that some animals use thermal features in surprising ways. In winter, for example, certain warm ground areas remain snow-free and can provide early vegetation growth, which may attract grazers and the predators that follow them. But perhaps the most scientifically unique biological component of Yellowstone is not its large mammals. It is its microbial life. In the colorful hot springs of places like Grand Prismatic Spring in the Midway Geyser Basin, we see mats of thermophilic organisms that thrive in extreme temperatures. Many of these microbes are bacteria, and archaea adapted to specific thermal and chemical niches. Their pigments create vivid bands of orange, yellow, and green, and their distribution reflects temperature gradients and water chemistry. In a sense, these microbial communities are living maps of geothermal conditions. The hydrothermal system itself is a major topic, because it is directly connected to the volcanic heat source. Yellowstone contains more than 10,000 hydrothermal features, including geysers, hot springs, mud pots, and fumaroles. The most famous geyser, Old Faithful, is located in the Upper Geyser Basin. Its predictability is tied to the plumbing of water and steam beneath the surface. Geysers require a combination of heat, water, and a restricted conduit system that allows pressure to build until an eruption occurs. This is not random behavior. It is physics, geology, and fluid dynamics playing out on a human timescale. To understand why Yellowstone has such a massive hydrothermal system, we need to consider the heat flow. The region is underlain by partially molten rock, and that magma transfers heat into the surrounding crust. Groundwater circulates downward through fractures, becomes heated, and returns to the surface. The chemistry of that water changes depending on the rocks it interacts with, and the surface features we see are expressions of that chemical evolution. Acidic waters can break down rock into clays, creating mud pots. Neutral to alkaline waters can deposit silica, forming sinter terraces like those seen at Mammoth Hot Springs. Although Mammoth is somewhat distinct because it is driven by limestone and travertine deposition, it still fits into the broader hydrothermal framework of Yellowstone. Now, let's address the central concern that draws so much attention, the volcanic hazard. Yellowstone has experienced 3 major caldera forming eruptions in the past 2.1 million years. The oldest of these occurred about 2.1 million years ago and produced the Huckleberry Ridge Tuff. The second occurred about 1.3 million years ago and produced the Mesa Falls Tuff. The most recent major caldera to forming eruption occurred about 631,000 years ago and produced the Lava Creek Tuff. Each of these eruptions was enormous and each reshaped the region. The Lava Creek eruption, for example, spread ash across much of North America. These events are part of why Yellowstone is classified as a high-consequence volcanic system. However, it is essential to understand the timescales involved. The interval between these major eruptions is measured in hundreds of thousands of years, not decades or centuries. The existence of past massive eruptions does not mean another one is imminent. In fact, the more common volcanic activity in Yellowstone's recent history has been lava flows, not supereruptions. Yellowstone has produced rhyolitic lava flows after the last caldera collapse, and those flows built domes and plateaus across parts of the park. These eruptions are still significant, but they are very different from a caldera-forming event. Yellowstone is also tectonically active. Earthquakes occur frequently in the region, often in swarms. These swarms can be linked to movement of fluids in the hydrothermal system, shifting stresses in the crust, or magmatic processes at depth. The Yellowstone region sits near the boundary of the basin and Range Province, where the crust is being stretched. That extension interacts with the hotspot's heat and magma supply, creating a dynamic environment. Ground deformation, measured by GPS and satellite radar, shows that parts of the caldera rise and fall over time, sometimes by centimeters per year. This breathing of the ground reflects changes in pressure from magma and hydrothermal fluids. If you're sitting in a lecture hall, you might be asking, what is the current state of the magma system? The answer is that Yellowstone's magma is not a single, giant molten chamber waiting to erupt. It is better described as a complex mush zone, where partially molten rock exists alongside crystals and solidified material. Geophysical imaging suggests that melt percentages vary, and much of the magma is not in a fully eruptible state. That said, the presence of melt and heat is enough to maintain the hydrothermal system and to produce occasional volcanic activity over geologic time. So in this first chapter, we've established the framework. Yellowstone is a hotspot-driven volcanic field with a large caldera, a massive hydrothermal system, and an ecosystem shaped by these forces. We've placed it geographically across Wyoming, Montana, and Idaho, and biologically we've introduced species like bison, Canis lupus, Cervus canadensis, Ursus arctos horribilis, and microbial thermophiles that define the park's extreme environments. We've also begun to outline the volcanic history that makes Yellowstone globally significant. In the next chapter, we will move deeper into the geology of the hotspot itself. We will discuss mantle plumes, the evidence for Yellowstone's deep heat source, and how magma evolves chemically as it rises through the crust. This will help us understand why Yellowstone erupts the types of magma it does, and why the system behaves the way it does today. Chapter 2. The Yellowstone hotspot and the chemistry of a supervolcano. Let's begin this chapter by revisiting a central question in Yellowstone science. What exactly is powering all of this? We have already established that Yellowstone is associated with a hotspot, and that hotspot is responsible for the volcanic and hydrothermal activity that defines the region. But in a lecture setting, we need to treat hotspot as more than a label. We need to unpack the mechanism, the evidence, and the implications for magma generation beneath the continental crust. In the simplest terms, a hotspot is a region where heat from the mantle rises toward the surface more persistently than in surrounding areas. The most famous hotspot example is Hawaii, which sits in the middle of an oceanic plate and builds volcanic islands. Yellowstone is more complicated because it sits beneath continental crust, which is thicker, chemically diverse, and structurally complex. This matters because continental crust interacts with magma in ways that can dramatically change the magma's composition, viscosity, and eruptive behavior. The hypothesis most commonly associated with Yellowstone is that a mantle plume, meaning a column of hot, buoyant mantle material, is rising from deep within the Earth. Some plume models suggest origins near the core mantle boundary, while other models propose a shallower mantle source with complex convection patterns. The reality is that the exact geometry and depth of Yellowstone's mantle anomaly is still debated. However, what is not debated is that the Yellowstone region has anomalously high heat flow, widespread volcanism along a track extending back millions of years, and geophysical evidence of hot material beneath the crust. Those observations require a sustained heat source. Whether we call it a plume, a hotspot, or a mantle upwelling, the physical effect is similar. Hotter than average mantle is producing melt that rises and feeds the volcanic system. One of the strongest lines of evidence for a hotspot track is the chain of calderas and volcanic deposits across the Snake River Plain. If you travel from Yellowstone southwestward through Idaho, you pass regions that were once above the hotspot millions of years ago. This is not a subtle feature. The Snake River Plain is a broad volcanic corridor, and its age progression matches the motion of the North American plate. In other words, the plate is moving. The heat source remains relatively fixed, and the surface record preserves that movement. This is why Yellowstone is often described as the current location of the hotspot, rather than an isolated volcanic anomaly. Now, in terms of magma chemistry, Yellowstone's eruptions are dominated by rhyolite. Rhyolitic magma is high in silica, often above 70% SiO2, and that high silica content makes the magma viscous. Viscosity is a key factor in explosive eruptions because viscous magma traps gas more effectively than fluid magma. When gas cannot escape gradually, pressure builds, and the system is more likely to erupt explosively. This is why rhyolitic systems are often associated with caldera-forming eruptions, ash flows, and widespread ignimbrite deposits. Yellowstone's major eruptions, including the Lava Creek Tuff event, are classic examples of large-volume rhyolitic volcanism. But here's the important scientific point. Rhyolite does not usually come straight from the mantle. The mantle typically produces basaltic magma, which is lower in silica and higher in magnesium and iron. Basalt is hot, fluid, and relatively low viscosity. So how do we get from basalt in the mantle to rhyolite in the crust? The answer involves a combination of processes including fractional crystallization, crustal melting, and magma mixing. Yellowstone is essentially a chemical processing system where mantle-derived basalt provides heat and material, and the continental crust contributes additional silica and evolved components. Fractional crystallization is one of the key mechanisms. As basaltic magma rises into the crust and begins to cool, minerals crystallize out of the melt. Those crystals often include olivine, pyroxene, and plagioclase, which preferentially remove magnesium, iron, and calcium from the melt. As those elements are removed, the remaining liquid becomes enriched in silica, sodium, potassium, and other incompatible elements. Over time, this process can evolve a magma from basaltic toward more intermediate and eventually rhyolitic compositions. But in a continental setting like Yellowstone, this is only part of the story. The continental crust itself can melt under the right conditions. If basaltic magma intrudes into the crust repeatedly, it can act like a heat source that slowly raises the temperature of surrounding rock. Over thousands to tens of thousands of years, that heat can cause partial melting of crustal material producing silica-rich melts. Those melts can accumulate and mix with evolved magmas, reinforcing the rhyolitic character of the system. This is one reason why Yellowstone's magma is so explosive compared to many basaltic volcanoes. The crust is not just a container, it is an active chemical participant. To make this more concrete, consider the physical structure beneath Yellowstone. Geophysical studies, including seismic tomography, indicate that there is a magma reservoir system beneath the caldera. This system is not a single hollowed chamber full of liquid magma. It is better described as a multi-level network of partially molten zones, crystal-rich mush regions, and pockets of higher melt fraction. Above this, the hydrothermal system circulates water through fractures and porous rock, extracting heat and transporting it to the surface. The magma system and the hydrothermal system interact, but they are not the same thing. The hydrothermal system is driven by heat, but it is largely water and steam, while the magma system is molten and semi-molten rock. This distinction matters because it helps us interpret Yellowstone's surface behavior. For example, ground deformation within the caldera can be caused by magma movement, but it can also be caused by changes in hydrothermal pressure. If fluids accumulate, expand, or shift location, they can lift the ground. If they drain or depressurize, the ground can subside. In a system as large as Yellowstone, these processes can happen repeatedly, creating cycles of uplift and subsidence over years to decades. The public sometimes interprets this as a sign that an eruption is imminent, but in many cases it reflects fluid dynamics rather than magma ascent. Let's now connect this back to the term supervolcano. A supereruption requires not only a large magma volume, but also magma that is sufficiently melt-rich, gas-charged, and connected in a way that allows a massive eruption to propagate. A mush zone with low melt fraction is not easily eruptible. It may contain enormous amounts of magma in a broad sense, but much of it may be locked up in crystals and solid frameworks. For a major eruption to occur, melt fractions must increase and the system must become more interconnected. That typically requires additional heat input, magma recharge, and time. So the size of the system alone does not determine the likelihood of eruption. We should also discuss the eruptive products that Yellowstone has produced, because they reveal the physics of past events. The Lava Creek Tuff, for example, is an ignimbrite deposit. Ignimbrites form from pyroclastic density currents, which are fast-moving, ground-hugging flows of hot ash, pumice, and gas. These flows can travel tens to hundreds of kilometers from the source and can deposit thick sheets of welded volcanic material. The Huckleberry Ridge Tuff and Mesa Falls Tuff are similar products from earlier caldera-forming eruptions. These deposits tell us that Yellowstone's major eruptions were not just explosive in the sense of ash clouds. They involved catastrophic, sustained pyroclastic flows that reshaped the landscape. Following the caldera-forming eruptions, Yellowstone entered phases of post-caldera volcanism, producing rhyolitic lava flows and domes. These eruptions are less dramatic than super-eruptions, but they still represent large volumes of viscous lava moving across the landscape. Rhyolite flows can be thick and slow-moving, forming steep-sided domes and rugged terrain. They are not typically associated with long, fluid lava rivers like basalt. Instead, they build up as piles of blocky, glassy rock, often fractured and unstable. In Yellowstone, many of these rhyolitic flows occurred between about 170,000 and 70,000 years ago, though volcanic activity in the broader region spans a longer interval. Now, Yellowstone's chemistry and heat also shape the biology in ways that are worth mentioning. Even in a volcanology-focused lecture, thermal areas create microhabitats that remain warmer year-round. In winter, when much of the park is snow-covered, bison may congregate near geothermal basins because the snow melts and exposes grasses. Similarly, elk may use lower elevation valleys with easier access to forage. Predators such as wolves and coyotes can take advantage of these concentrations. This is a subtle but important point. Geothermal heat is not only a geological phenomenon, it influences ecological patterns. The hydrothermal chemistry also produces extreme conditions that only specialized organisms can tolerate. In acidic hot springs, microbial communities may include thermophilic archaea that thrive at high temperatures and low pH. In more neutral hot springs, photosynthetic bacteria can form layered mats. These organisms are not just visually interesting, they are biologically significant because they show how life can adapt to conditions that resemble early Earth environments, and they provide analogues for astrobiology research. Yellowstone's thermal basins have contributed to major discoveries in microbiology, including enzymes used in biotechnology, such as DNA polymerases derived from thermophiles. Let's also address a common misconception, that Yellowstone is one volcano that will explode. In reality, Yellowstone is a volcanic plateau with multiple eruptive centers, a complex caldera structure, and widespread hydrothermal activity. It is not best understood as a single vent. It is a region where the crust is thermally and chemically altered over a vast area. The hazard profile is therefore multi-layered. The most catastrophic scenario is a supereruption, but more probable events include smaller rhyolitic eruptions, hydrothermal explosions, lava flows, and earthquake swarms. Hydrothermal explosions are especially relevant because they can occur without magma reaching the surface. If hot water becomes trapped, pressure can build until the ground ruptures, producing localized craters and ejecting rock and steam. These events are smaller than volcanic eruptions, but they can be dangerous in geothermal areas. So, what should we take away from this chapter? Yellowstone is powered by a sustained mantle heat source, expressed at the surface through volcanism and hydrothermal activity. The magma system is dominated by evolved rhyolite, produced through a combination of mantle basalt input, fractional crystallization, and crustal melting. The result is a volcanic field capable of extremely large eruptions, but also characterized by complex long-term processes that do not operate on human timescales in the way popular narratives suggest. In the next chapter, we will shift from deep earth processes to surface expressions. Specifically, we will examine the Yellowstone caldera in more detail, including how it formed, what its boundaries represent, and how modern monitoring reveals the caldera's ongoing deformation and seismicity. This will give us a clearer picture of how scientists track changes in the system and how we interpret those changes responsibly. Chapter 3. The Yellowstone caldera, collapse events, and modern ground deformation. In this chapter, we are going to focus on one of the most important structural features in the Yellowstone volcanic system, the caldera itself. The word caldera is often used casually, sometimes as if it simply means crater, but in volcanology it refers to a specific type of collapse structure formed by large volume eruptions. Yellowstone's caldera is not merely a scenic basin. It is the surface expression of a major volcanic event, and it is also the framework within which much of the park's hydrothermal activity and seismic behavior takes place. To begin, let's define the mechanism of caldera formation. A caldera forms when a magma reservoir is partially emptied by an eruption large enough to remove a significant amount of material from beneath the surface. As magma is expelled, the roof of the reservoir loses support. The overlying rock collapses downward, often along ring fractures, producing a broad depression. This is different from a simple volcanic crater, which might form by explosive excavation at a vent. Calderas are collapse features, and their size is typically proportional to the scale of the eruption that created them. Yellowstone's most recent major caldera-forming eruption occurred approximately 631,000 years ago. This event produced the Lava Creek Tuff, a massive ignimbrite deposit that spread across large areas of the western United States. The eruption was so large that it led to the collapse of the ground surface over a region roughly 45 miles long and 30 miles wide. That collapse created the Yellowstone caldera we recognize today. It is important to note that caldera boundaries are not always obvious on the ground. Over time, erosion, sedimentation, and later volcanic activity can soften the topography. Yellowstone's caldera is therefore not a dramatic bowl-shaped crater. It is a broad, geologically defined structure that can be mapped through rock units, faults, and geophysical measurements. Within the caldera, we see evidence of continued volcanism after the collapse event. This is a common feature in caldera systems. After a major eruption, the magma system does not necessarily shut down. Instead, it can continue to generate melt, often producing post-caldera rhyolite flows, domes, and resurgent uplift. Resurgence refers to the slow upward movement of the caldera floor as magma intrudes or pressurizes the crust beneath it. In Yellowstone, resurgent domes are a key part of the landscape, and they help explain why some regions within the caldera are elevated relative to others. Two major resurgent domes are typically discussed in Yellowstone: the Mallard Lake Dome and the Sour Creek Dome. These domes represent areas where the caldera floor has been uplifted by magmatic and hydrothermal processes. If you examine maps of Yellowstone's geology, you will see that these domes correspond to broad zones of uplift and deformation. The existence of these domes tells us that Yellowstone's magma system remained active after the Lava Creek eruption and that it continues to influence crustal stresses today. Now, when we talk about deformation at Yellowstone, we are referring to measurable changes in the elevation and shape of the ground surface over time. Yellowstone is monitored continuously using GPS stations, satellite radar interferometry, and leveling surveys. These tools allow scientists to detect uplift and subsidence at the scale of centimeters. One of the most striking aspects of Yellowstone's caldera is that it does not remain static. Over decades, parts of the caldera rise, then fall, then rise again. This behavior has been described as the caldera breathing, although that term is more metaphor than mechanism. The physical causes of uplift and subsidence in Yellowstone can be divided into two broad categories: magmatic processes and hydrothermal processes. Magmatic processes involve the movement or pressurization of magma at depth. If magma intrudes into a shallow reservoir or increases pressure in a mush zone, it can push the overlying rock upward. Hydrothermal processes involve changes in the distribution, temperature, and pressure of fluids like hot water and steam. If fluids become trapped or heated, they expand, increasing pressure and potentially causing uplift. If fluids migrate away or depressurize, the ground can subside. Distinguishing between these causes is not always straightforward, and that is one reason why Yellowstone is such a valuable natural laboratory. It forces geoscientists to integrate multiple datasets. Seismicity patterns, gas emissions, temperature measurements, and deformation data all contribute to interpretation. A deformation signal alone does not automatically imply magma is rising toward the surface. In many cases, the deformation may be largely driven by hydrothermal fluid changes. Yellowstone is also one of the most seismically active regions in the United States, at least in terms of frequent small earthquakes. Most earthquakes in the region are minor and not felt by visitors, but they occur constantly. Yellowstone experiences earthquake swarms, which are clusters of earthquakes occurring in a localized region over a short period of time. Swarms can involve dozens, hundreds, or even thousands of events. Unlike typical tectonic sequences where one main shock is followed by aftershocks, swarms often lack a single dominant event. This pattern is common in volcanic and geothermal regions because swarms can be triggered by fluid movement in fractures, pressure changes, or small-scale fault adjustments. A major geographic feature relevant to Yellowstone's seismicity is the Hebgen Lake region, northwest of the park, and the broader tectonic environment of the Basin and Range province. Yellowstone lies near the transition between the Rocky Mountain region and the Basin and Range, where the crust is being stretched. This extension creates normal faults and contributes to earthquake activity. The interaction between tectonic extension and hotspot-related thermal weakening makes the crust more deformable and fractured. Those fractures in turn provide pathways for hydrothermal circulation. Now let's discuss the caldera boundaries and the internal structure in more detail. Calderas often have ring faults or ring fractures that mark zones of weakness where collapse occurred. These structures can remain active over time, acting as conduits for magma intrusions and hydrothermal fluids. In Yellowstone, many hydrothermal basins are located within or near the caldera boundaries, suggesting that structural controls influence where hot water can rise to the surface. The Upper Geyser Basin, Midway Geyser Basin, and Lower Geyser Basin are all located within the general caldera region, and their activity is linked to heat flow and groundwater movement through fractured rock. Yellowstone Lake is also significant in this context. The lake sits partly within the caldera and occupies a region shaped by both volcanism and glaciation. Beneath Yellowstone Lake, there are hydrothermal vents and areas of active fluid discharge. The lake floor contains volcanic and hydrothermal features, including domes and explosion craters. These underwater geothermal systems are less visible to visitors, but are important for understanding the full extent of Yellowstone's activity. The presence of hydrothermal vents under the lake also has implications for water chemistry, sedimentation, and localized hazards. We should now return to the collapse event itself, because understanding the caldera requires understanding the eruption that created it. The Lava Creek eruption was not a single momentary explosion. It was a sustained eruptive sequence that likely involved multiple phases, including the eruption of ash columns and the generation of pyroclastic density currents. These currents would have swept across the landscape, depositing thick layers of ash and pumice that later welded into tuff. The collapse of the caldera would have occurred as the eruption drained magma from beneath the surface. In many caldera systems, collapse can occur in stages, with blocks dropping along faults rather than the entire region collapsing at once. This creates a complex internal structure with tilted blocks and fault-bounded segments. Following collapse, the caldera floor can become a site of sediment accumulation. Over time, lakes may form in the depression, rivers may deposit sediments, and hydrothermal alteration may change the mineralogy of rocks. Hydrothermal alteration is particularly important because hot fluids can chemically transform volcanic rocks into clays and other minerals, weakening the rock and changing permeability. This affects both the stability of the ground and the pathways for fluid flow. In a hydrothermal area, you often see ground that is bright white, yellow, or orange due to sulfur deposits and altered clays. These surface colors are not just aesthetic, they indicate active chemical reactions. This brings us to an important hazard category that is sometimes overlooked in popular discussions: hydrothermal explosions. A hydrothermal explosion occurs when hot water trapped beneath the surface flashes to steam, rapidly expanding and breaking apart rock. This can happen when pressure drops suddenly, when a blockage is removed, or when heat input changes. Hydrothermal explosions do not require new magma to reach the surface. They are driven by the existing heat of the system and the behavior of water and steam in confined spaces. Yellowstone has a history of hydrothermal explosions, and some of the craters in the park, including features near Yellowstone Lake, may be related to such events. While these explosions are usually localized, they can be violent and dangerous within a limited radius. Now, let's connect this geological structure to the living landscape. The Caldera Basin and its surrounding valleys provide habitat for many of Yellowstone's large mammals. The Hayden Valley, for example, is a broad open area where visitors often see bison, elk, and sometimes grizzly bears foraging or moving across the landscape. The Lamar Valley, farther north, is often called America's Serengeti because of its visibility and wildlife density. Wolves are frequently observed there, along with pronghorn and mule deer. These valleys exist in part because of the geological history that created broad basins and sediment-filled lowlands. Even the distribution of vegetation is influenced by caldera processes. Soils derived from volcanic ash can be fertile and support grasslands, while hydrothermally altered soils may be acidic and less supportive of plant growth. Geothermal heat can extend the growing season in localized patches, influencing where animals graze in winter. This is why Yellowstone's ecology cannot be separated from its geology. The caldera is not simply a volcanic scar. It is an organizing structure for ecosystems. We should also consider the timescales of caldera evolution. Yellowstone's caldera formed 631,000 years ago, but the system continues to evolve. Resurgence, faulting, hydrothermal alteration, and sedimentation have all modified the caldera since its formation. When scientists monitor deformation today, they are observing processes that may be part of long-term cycles. Some uplift events may represent magma recharge, while others may represent fluid accumulation. Earthquake swarms may reflect fluid migration along faults. Over time, these processes shape the caldera's internal plumbing. One of the key challenges in Yellowstone science is interpreting signals in a system where multiple processes overlap. For example, an earthquake swarm might occur at the same time as ground uplift. Is the uplift caused by magma intrusion that also triggered earthquakes? Or is the uplift caused by hydrothermal pressurization that also increased stress on faults? These questions require integrated modeling and careful analysis. This is why Yellowstone is monitored so closely, not because an eruption is expected imminently, but because it is a complex active system where understanding requires continuous observation. To summarize this chapter, the Yellowstone caldera is the result of a massive collapse event associated with the Lava Creek Tuff eruption. The caldera contains resurgent domes, active deformation, frequent seismicity, and an extensive hydrothermal system. Ground uplift and subsidence reflect changes in subsurface pressure, driven by both magma and fluids. Earthquake swarms reveal ongoing fracture activity and fluid movement. Hydrothermal explosions represent a real and localized hazard that does not require new magma to erupt. And throughout all of this, the caldera's structure shapes the landscape and the ecosystems that depend on it. In the next chapter, we will move from the caldera structure into the hydrothermal system in a more detailed and mechanistic way. We will examine how geysers work, why Yellowstone has such an extraordinary density of hydrothermal features, and what the chemistry of these waters can tell us about conditions deep underground. Chapter 4. The Hydrothermal Engine, Geyser Physics, and Yellowstone Surface Chemistry. In this chapter, we are going to shift our focus from the large-scale volcanic structure of Yellowstone to one of its most famous and scientifically revealing features, the hydrothermal system. Yellowstone is, in many ways, the most active hydrothermal region on Earth. It contains thousands of hot springs, geysers, mud pots, fumaroles, and thermal pools. These features are not simply surface curiosities. They are the visible output of a heat and fluid engine that connects groundwater circulation to deep geothermal heat, and in some cases to the margins of magma bodies beneath the caldera. To understand Yellowstone's hydrothermal system, we need to start with three essential requirements. The first is a heat source, which Yellowstone clearly has in the form of shallow magma and hot rock beneath the crust. The second is water, which is supplied by rain and snowmelt that infiltrate the ground. The third is permeability, meaning the presence of fractures, faults, porous rock layers, and pathways that allow water to circulate downward and then return upward. If any of these three conditions is missing, you do not get a hydrothermal field at Yellowstone's scale. Yellowstone is unusual because all three conditions are present in abundance, and they overlap across a massive area. The hydrothermal system begins with cold water at the surface. Snowmelt and rainfall seep into the ground and travel downward through cracks in volcanic rock and sediment. As this water descends, it is gradually heated by hot rock. The deeper it goes, the higher the temperature and pressure become. At depth, water can remain liquid at temperatures above the normal boiling point because pressure increases with depth. When this hot water rises toward the surface, pressure decreases. At some point, the water may boil, flash into steam, or release dissolved gases. The combination of rising hot water and phase changes is what drives many of Yellowstone's surface features. A hot spring is the simplest expression of this system. Hot water rises to the surface and flows out continuously. The temperature, chemistry, and appearance of a hot spring depend on its heat input, its water source, and the minerals it interacts with underground. Some springs are clear and blue, indicating relatively clean water with minimal suspended particles. Others are cloudy or colorful due to microbial mats, mineral precipitation, or suspended sediments. The large, visually striking springs, such as Grand Prismatic Spring in the Midway Geyser Basin, are often used as symbols of Yellowstone, but from a scientific standpoint they are also indicators of stable heat flow and sustained circulation pathways. Now, geysers are more complicated. Yellowstone contains more geysers than the rest of the world combined. That statement alone should prompt a question: why here? The answer is that geysers require a very specific plumbing system. They are not simply hot springs that erupt. They require constricted channels, chambers, and a geometry that allows pressure to build. In a geyser system, water fills underground cavities and conduits. Heat from below warms the water. As the temperature rises, some water begins to boil, producing steam bubbles. In an open system, that steam might escape gradually, but in a geyser, the geometry restricts flow, trapping steam and increasing pressure. As pressure builds, the boiling point of water increases. This allows water in the system to become superheated relative to surface conditions. Eventually, the system reaches a tipping point. When boiling becomes vigorous enough, water is forced upward, pressure drops rapidly, and a chain reaction occurs. More water flashes to steam, expanding violently and ejecting water out of the vent. That is the eruption. Afterward, the system refills and begins the heating process again. This cycle is not magical. It is thermodynamics and fluid mechanics operating in a natural conduit network. Old Faithful, located in the Upper Geyser Basin, is the most famous example because it erupts with relatively regular timing. However, Old Faithful is not the largest geyser. Steamboat Geyser, located in the Norris Geyser Basin, is currently the tallest active geyser in the world, capable of eruptions that can exceed 90 meters in height. The difference between these geysers reflects differences in plumbing geometry, water supply, and heat input. Some geysers are predictable, while others are irregular. In many cases, small changes in the underground system, including mineral deposition or seismic disturbance, can alter eruption intervals. This leads us to an important point. Yellowstone's hydrothermal system is dynamic. It changes over time. Earthquakes can open fractures, close pathways, or change pressure conditions. Mineral precipitation can clog conduits. Shifts in groundwater supply can alter water levels and temperatures. This is why geyser behavior can change from year to year, and why new features sometimes appear while others become dormant. Let's now discuss the chemistry of Yellowstone's thermal waters, because this chemistry provides direct evidence of underground conditions. One of the most important chemical distinctions in Yellowstone is between acidic and alkaline thermal waters. Acidic waters are often associated with fumaroles and mudpots, where volcanic gases such as hydrogen sulfide rise toward the surface. When hydrogen sulfide interacts with oxygen, it can form sulfuric acid. This acid can break down rock into clay, producing the thick, bubbling mud characteristic of places like the mud volcano area. In these environments, the landscape can appear gray, white, or yellow, and the smell of sulfur is often strong. Alkaline waters, in contrast, are more common in many of Yellowstone's large hot springs and geyser basins. These waters can dissolve silica from volcanic rock at high temperatures. When the water reaches the surface and cools, silica can precipitate out, forming sinter deposits. Sinter is a hard, white to gray mineral crust that can build terraces and platforms around geysers and hot springs. Over time, these deposits can preserve the outlines of ancient thermal features, creating a geologic record of hydrothermal activity. The presence of silica sinter is one reason geyser basins have such distinctive terrain. The ground can be hard in some areas, fragile in others, and often thinly crusted over hot water channels. This is also why staying on boardwalks is not merely a park rule. It is a safety requirement in an environment where boiling water and unstable ground exist just below the surface. Another chemical component to consider is dissolved gases. Hydrothermal waters can carry carbon dioxide, hydrogen sulfide, methane, and other gases. These gases can influence pH, mineral precipitation, and microbial metabolism. In some areas, carbon dioxide can accumulate in low spots, creating localized hazards for small animals. While this is not a dominant threat to visitors, it illustrates how geothermal systems can produce complex and sometimes subtle risk factors. Now, the biological dimension of hydrothermal chemistry is one of the most scientifically famous aspects of Yellowstone. Many thermal pools are ringed by microbial mats, and the color patterns in these mats often correspond to temperature gradients. Thermophilic organisms, meaning heat-loving organisms, occupy niches where most life would not survive. In hotter zones, you find organisms adapted to near-boiling temperatures. In cooler zones, you may find photosynthetic bacteria that can use sunlight. The result is a layered ecosystem that is, in effect, organized by temperature. One well-known example is the bacterium Thermus aquaticus, originally discovered in Yellowstone hot springs. This organism produces a heat-stable DNA polymerase, which became central to the development of PCR, the polymerase chain reaction, a technique that revolutionized molecular biology. This is an important reminder that Yellowstone's value is not only aesthetic or recreational. It has directly contributed to scientific technology and medicine through discoveries in extremophile biology. But the hydrothermal system is also destructive. Hydrothermal alteration can weaken rock by transforming it into clays. This can destabilize slopes, contribute to landslides, and alter the mechanical strength of the ground. In a caldera system, hydrothermal alteration is often concentrated along faults and fractures where fluids circulate most intensely. This is one reason why the distribution of hydrothermal features is not random. It is controlled by the structure of the crust. Faults, ring fractures, and fractured lava flows create pathways for water and steam to rise. The Norris Geyser Basin is particularly important for understanding Yellowstone's hydrothermal variability. Norris is one of the hottest and most dynamic thermal areas in the park. It sits near the intersection of major fault systems, and it often exhibits rapid changes in thermal activity. Scientists pay close attention to Norris because it can show shifts in temperature, chemistry, and geyser behavior that may reflect changes in the deeper hydrothermal plumbing. We should also mention Mammoth Hot Springs, located near the northern entrance of the park. Mammoth is distinct from many other Yellowstone thermal areas because its terraces are formed primarily from travertine, a type of calcium carbonate deposit. The travertine forms because hot water dissolves limestone at depth and then precipitates calcium carbonate when it reaches the surface and releases carbon dioxide. The result is a rapidly changing landscape of white terraces and cascading mineral formations. Mammoth demonstrates that Yellowstone's hydrothermal features are not all driven by the same rock chemistry. The bedrock composition matters. Now, one of the key questions in Yellowstone hydrothermal science is how directly the hydrothermal system connects to magma. In some cases, hydrothermal fluids may circulate close to shallow magma bodies or hot intrusions. In other cases, the heat source may be hot rock rather than molten magma. The distinction matters for interpreting signals like temperature changes, gas emissions, or new thermal activity. A change in hydrothermal output does not necessarily indicate magma is rising. It may indicate a shift in fluid pathways, pressure changes, or seismic disruption. However, Yellowstone's hydrothermal system is ultimately sustained by volcanic heat, and that means it is indirectly tied to the magma system, even when magma is not actively moving upward. This is why hydrothermal monitoring is part of volcanic hazard assessment. Changes in hydrothermal activity can sometimes accompany changes in subsurface conditions. Scientists monitor temperature, water chemistry, gas emissions, and deformation to build a comprehensive picture. We also need to discuss hydrothermal explosions again, but this time in more detail. A hydrothermal explosion occurs when pressurized hot water flashes into steam, expanding rapidly and fragmenting rock. This can excavate craters, eject blocks of rock, and produce localized blast zones. Hydrothermal explosions can occur with little warning because they do not require magma to erupt. They require a combination of heat, water, and confinement. Yellowstone has experienced hydrothermal explosions in the past, and evidence of these events includes explosion craters and deposits of fragmented rock. Some features near Yellowstone Lake may be related to such processes, and the lake itself contains hydrothermal vents that demonstrate ongoing activity beneath the water. From a hazard perspective, hydrothermal explosions are more probable than a volcanic eruption on human timescales, even though they are smaller. They represent the kind of event that could occur within a thermal basin, affecting a localized area. This is another reason why Yellowstone is managed carefully and monitored continuously. To summarize this chapter, Yellowstone's hydrothermal system is driven by the interaction of groundwater with volcanic heat. Hot springs represent continuous discharge, while geysers require specialized plumbing systems that allow pressure cycles to build and release. Chemistry distinguishes acidic systems dominated by volcanic gases from alkaline systems that deposit silica sinter. Microbial life thrives in these extreme environments, with organisms like Thermus aquaticus having major scientific importance. Hydrothermal alteration changes rock strength and permeability, shaping the distribution and evolution of thermal basins. And hydrothermal explosions represent a significant localized hazard that arises from the physics of water and steam rather than direct magma eruption. In the next chapter, we will return to the deeper volcanic system and examine Yellowstone's eruption history in more detail. We will look at the three major caldera-forming eruptions, what they produced, how scientists reconstruct their timelines, and what the deposits tell us about the dynamics of supereruptions. Chapter 5. Yellowstone's three major eruptions and the anatomy of a supereruption. In this chapter, we are going to examine Yellowstone's eruption history through the lens of its three major caldera to forming events. These eruptions are the reason Yellowstone is frequently described as a supervolcano, and they provide one of the clearest examples on Earth of how large silicic volcanic systems evolve, erupt, and reshape continental landscapes. Our goal here is not to sensationalize Yellowstone's past, but to understand it in a structured way, using the evidence preserved in volcanic deposits, geochronology, and caldera architecture. Yellowstone's three major caldera-forming eruptions occurred approximately 2.1 million years ago, 1.3 million years ago, and 631,000 years ago. Each eruption produced a massive ignimbrite deposit, which is a rock formed from pyroclastic density currents that travel across the ground at high speed. These currents consist of hot gas, ash, pumice, and fragmented rock. Unlike an eruption column that rises into the atmosphere and spreads ash widely, pyroclastic density currents are ground-hugging flows that can devastate large regions near the volcano. In Yellowstone's case, the scale was enormous. The deposits from these events cover wide areas of the western United States and serve as markers of major volcanic episodes. The first of these major eruptions occurred about 2.1 million years ago and produced the Huckleberry Ridge Tuff. This eruption is often considered one of the largest known volcanic eruptions in Earth's recent geological history. It expelled an extraordinary volume of material, and the resulting caldera collapse created what is sometimes referred to as the Island Park caldera, located west of the modern Yellowstone caldera. The Huckleberry Ridge Tuff is an ignimbrite deposit that can be traced across large areas, and it provides evidence of a sustained eruption sequence that likely lasted days to weeks. When we talk about eruptions of this magnitude, it is important to imagine not a single blast, but a prolonged period of continuous volcanic discharge with repeated pyroclastic flows and ash emissions. The second major eruption occurred about 1.3 million years ago and produced the Mesa Falls Tuff. This event created the Henry's Fork caldera, also west of the modern Yellowstone caldera. While smaller than the Huckleberry Ridge event, it was still massive by any reasonable standard. The Mesa Falls Tuff is another ignimbrite deposit, and its presence shows that Yellowstone's hotspot system has produced repeated large eruptions over time as the North American plate moved over the heat source. The caldera formed by this eruption is part of the larger volcanic track that extends along the Snake River Plain. The third and most recent major caldera to forming eruption occurred about 631,000 years ago and produced the Lava Creek Tuff. This eruption created the modern Yellowstone caldera, centered within what is now Yellowstone National Park. The Lava Creek event is often the one most discussed because it defines the current caldera structure and because it is the most recent of the three. It also provides the most direct link between Yellowstone's deep magma system and the landscape that visitors see today. The Lava Creek Tuff is widespread, and ash from the eruption was dispersed across much of North America. Even today, volcanic ash layers from this eruption can be found far from Yellowstone, preserved in sedimentary sequences and used as time markers in geologic studies. Now, how do we reconstruct the dynamics of these eruptions? The primary evidence comes from the deposits themselves. Ignimbrite deposits can be analyzed for thickness, welding intensity, pumice content, and mineral composition. Welding refers to the process by which hot ash and pumice particles fuse together after deposition. In a high-temperature pyroclastic flow, the deposited material may remain hot enough to weld, forming a dense, coherent rock. Variations in welding can indicate differences in temperature, flow thickness, and emplacement conditions. These details help volcanologists infer the energy and structure of the eruption. Another critical tool is geochronology, the science of dating rocks. Yellowstone's tuffs have been dated using methods such as argon-argon dating on volcanic minerals. This allows scientists to establish eruption ages with relatively high precision. These dates confirm that the three major eruptions are separated by hundreds of thousands of years, which is an important point for understanding recurrence intervals. While the timing is not perfectly regular, the spacing between these events is on the order of 600,000 to 800,000 years. That does not imply a predictable cycle, but it does provide context for how rare these eruptions are on human timescales. To understand what makes a supereruption, we need to examine the physical requirements. A supereruption requires a large volume of magma, typically rhyolitic, that is sufficiently molten, gas-rich, and connected in a way that allows rapid evacuation. In a magma reservoir, rhyolitic melt can accumulate over long periods, evolving chemically and building volatile content. Volatiles include water vapor, carbon dioxide, sulfur species, and other gases dissolved in the melt under pressure. As magma rises or pressure decreases, these gases exsolve, forming bubbles. If the magma is viscous, bubbles cannot escape easily, and pressure increases. This can lead to explosive fragmentation of magma into ash and pumice. But Yellowstone's magma reservoir is not a simple tank of liquid magma. As discussed earlier, it is more accurately described as a crystal-rich mush zone with pockets of higher melt fraction. Over time, melt can segregate from crystals and accumulate in zones of higher melt content. If those zones become sufficiently large and connected, they may become eruptible. Recharge from basaltic magma entering from below can add heat and volatiles, potentially increasing melt fraction and mobilizing the system. In this way, supereruptions are often associated with complex pre-eruptive processes that may involve magma recharge, mixing, and pressurization. One of the defining features of large caldera to forming eruptions is the collapse sequence. As magma is evacuated, the roof of the reservoir collapses. This collapse can occur in stages, with fault-bounded blocks dropping into the reservoir. The collapse itself can influence eruption dynamics, potentially sustaining pyroclastic flows and widening the eruptive vents. The result is often a ring fracture system around the caldera, which may later act as a conduit for post-caldera volcanism and hydrothermal circulation. Following caldera collapse, the volcanic system typically enters a post-caldera phase. In Yellowstone, this phase included eruptions of rhyolitic lava flows and domes. These eruptions are important because they demonstrate that Yellowstone remained volcanically active long after the last super-eruption. The caldera did not become dormant. Instead, it became the site of continued magma movement and surface eruptions, though on a smaller scale. Many of Yellowstone's post-caldera rhyolites erupted between roughly 170,000 and 70,000 years ago, forming flows that can be mapped across parts of the park. We should also discuss ash dispersal and climatic effects, because these are often highlighted in popular accounts of Yellowstone. A large eruption can inject ash and sulfur aerosols into the atmosphere, potentially affecting climate. However, the magnitude and duration of climatic effects depend on eruption composition, sulfur content, eruption column height, and atmospheric circulation. Yellowstone's eruptions certainly would have had regional to continental impacts, including heavy ashfall, disruption of ecosystems, and long-term landscape changes. Whether they produced global climatic shifts comparable to other major volcanic events is a more complex question. It is not enough to say supereruption equals global catastrophe. The details matter, and scientists evaluate those details through geochemical analysis and climate modeling. From a biological perspective, Yellowstone's eruption history also shaped ecosystems through habitat destruction and renewal. Ashfall can bury vegetation, alter soil chemistry, and affect water systems. Yet volcanic deposits can also create new soils over time, and volcanic landscapes can develop diverse habitats as they erode and weather. Yellowstone's modern ecosystems, including the grasslands where bison graze and the forests where elk migrate, exist on terrain shaped by repeated volcanic deposition and glacial modification. Predators such as wolves and bears occupy ecological niches that depend on these landscapes. Even smaller species, such as the American pika in rocky alpine areas, are indirectly tied to volcanic terrain and elevation patterns. It is also worth noting that Yellowstone's eruption history is intertwined with glaciation. During the Pleistocene, glaciers advanced and retreated across the Yellowstone region, carving valleys, depositing sediments, and modifying volcanic features. The interaction between volcanism and glaciation is complex. Glaciers can erode volcanic deposits, fill caldera basins with sediments, and influence groundwater flow. In turn, volcanic heat can melt ice locally and influence glacial behavior. The modern Yellowstone landscape is therefore the product of both fire and ice, shaped by eruptive events and glacial sculpting over hundreds of thousands of years. Now, in a lecture hall, one of the questions that often arises is whether Yellowstone is overdue for another supereruption. Scientifically, the concept of overdue is not a reliable way to think about volcanic systems. Volcanoes do not operate on a schedule like a clock. While we can estimate recurrence intervals from the geologic record, those intervals are not predictive. The magma system must reach certain physical conditions for a large eruption to occur, and those conditions depend on many variables, including heat input, magma recharge, melt fraction, volatile content, and crustal stress state. Yellowstone's monitoring data today does not indicate that a super-eruption is imminent. That does not mean it cannot happen in the distant future, but it does mean that current conditions are not consistent with an eruption in the near term. Instead, the more practical scientific approach is to understand Yellowstone as an active volcanic system with a spectrum of possible events. The largest events are extremely rare. Smaller volcanic eruptions, lava flows, and hydrothermal explosions are more likely on human timescales, though still not common. Earthquake swarms and ground deformation are frequent and are part of the normal behavior of the system. The challenge is to interpret these signals correctly and avoid conflating normal activity with impending catastrophe. To summarize this chapter, Yellowstone's three major caldera-forming eruptions produce the Huckleberry Ridge Tuff, Mesa Falls Tuff, and Lava Creek Tuff, each associated with massive ignimbrite deposition and caldera collapse. These eruptions were driven by large volumes of evolved rhyolitic magma, generated through long-term crustal processing and sustained heat input from the hotspot. The anatomy of a supereruption involves magma accumulation, volatile pressurization, explosive fragmentation, pyroclastic flows, and collapse into a caldera. After these major events, Yellowstone continued to erupt rhyolitic lava flows, and its landscape was further modified by glaciation and erosion. The system today remains active, but it does not behave like a ticking time bomb. It behaves like a long-lived volcanic field that requires careful scientific monitoring and responsible interpretation. In the next chapter, we will move from eruption history into the modern monitoring framework. We will discuss how scientists track Yellowstone today, including seismic networks, GPS deformation measurements, gas emissions, thermal monitoring, and how these datasets are used to evaluate volcanic hazards without relying on sensational narratives. Chapter 6. Monitoring Yellowstone today. Seismic networks, gas emissions, and volcanic forecasting. In this chapter, we are going to focus on Yellowstone as it exists right now, not as a dramatic historical event, but as an active system under constant scientific observation. Yellowstone is one of the most heavily monitored volcanic regions in the world. That monitoring exists for two reasons. First, Yellowstone is a high-consequence volcanic system, meaning that although large eruptions are rare, their impacts could be substantial. Second, Yellowstone is continuously active in smaller ways, through earthquakes, hydrothermal changes, and ground deformation. Monitoring allows scientists to understand baseline behavior and detect changes that might indicate evolving conditions underground. The primary organizations involved in Yellowstone monitoring include the Yellowstone Volcano Observatory, which is a collaboration between the U.S. Geological Survey, the University of Utah, the National Park Service, and other partners. The core principle behind this work is that volcanic systems provide signals before major changes occur. Those signals may not be simple, and they may not point to a single outcome, but they can be measured, analyzed, and interpreted using established physical models. Let's start with the most visible form of monitoring seismic networks. Yellowstone experiences thousands of earthquakes every year, most of which are small and go unnoticed by visitors. These earthquakes occur because the crust beneath Yellowstone is fractured, stressed, and constantly adjusting. In volcanic regions, earthquakes can be caused by tectonic fault movement, magma movement, or the movement of fluids such as hot water and steam. In Yellowstone, all three mechanisms are possible, and part of the scientific challenge is distinguishing among them. The University of Utah seismograph stations maintain a network of seismometers in and around Yellowstone. These instruments record ground vibrations and allow scientists to locate earthquakes in terms of their latitude, longitude, depth, and magnitude. By mapping earthquake locations over time, researchers can identify patterns such as swarms, fault alignments, and depth clusters. Yellowstone is especially known for earthquake swarms, which are episodes where many earthquakes occur in a short period of time in a concentrated area. Earthquake swarms are significant because they often indicate fluid movement. When fluids migrate through fractures, they can change pore pressure, reducing friction on faults and triggering small slips. In some cases, swarms may also be linked to magma intrusion, but in Yellowstone, many swarms are interpreted as hydrothermal or tectonic in origin. The distinction matters because a swarm does not automatically imply magma is moving toward the surface. In fact, Yellowstone's frequent swarms are part of its baseline behavior. Scientists evaluate swarms in context, looking at depth, migration patterns, and whether other signals, such as deformation or gas emissions, change at the same time. One of the most notable seismic events in Yellowstone's broader region was the 1959 Hebgen Lake earthquake, a magnitude 7.3 event that occurred northwest of the park. This earthquake caused dramatic ground deformation, landslides, and changes in hydrothermal features. While it was tectonic rather than volcanic, it illustrates how strongly earthquakes can influence Yellowstone's geothermal system. Large earthquakes can alter groundwater pathways, change spring discharge rates, and modify geyser behavior. This is an important reminder that Yellowstone's surface activity is sensitive not only to magma and heat, but also to crustal stress changes. Now, let's move to ground deformation monitoring. Yellowstone's caldera rises and falls over time, sometimes by several centimeters per year. This is measured using GPS stations installed across the park and surrounding region. GPS deformation data provide precise measurements of vertical and horizontal ground movement. In addition to GPS, scientists use satellite radar interferometry, often referred to as INSAR, which can detect subtle surface changes across wide areas. INSAR is particularly valuable because it provides spatial patterns of deformation, showing whether uplift is localized, broad, or shifting over time. The causes of deformation can be magmatic, hydrothermal, or a combination of both. Magmatic deformation might occur if magma intrudes into a shallow reservoir or if pressure increases in a partially molten zone. Hydrothermal deformation might occur if fluids become trapped, heated, or redistributed beneath the surface. Yellowstone's deformation history includes periods of uplift and subsidence, and the system does not show a simple long-term trend in one direction. Instead, it shows episodic changes, which suggests that the subsurface pressure system is dynamic and responsive. In a forecasting context, deformation is one of the most important signals, but it must be interpreted carefully. In many volcanic systems, rapid and sustained uplift accompanied by increasing seismicity and changing gas emissions can indicate magma intrusion. In Yellowstone, uplift alone is not enough to make that conclusion because hydrothermal pressure changes can also produce uplift. This is why Yellowstone monitoring is fundamentally multi-parameter. Scientists do not rely on a single dataset. They look for correlations among multiple signals. Gas emissions are another major monitoring component. Volcanic and hydrothermal systems release gases such as carbon dioxide, sulfur dioxide, hydrogen sulfide, methane, and helium. In Yellowstone, much of the gas release is dominated by carbon dioxide and hydrogen sulfide, reflecting the hydrothermal system's interaction with deep heat and volcanic gases. Measuring gas emissions can provide insight into the depth and nature of fluid sources. For example, changes in carbon dioxide flux might indicate changes in deep degassing or fluid pathways. Helium isotope ratios can also be informative, because mantle-derived helium has a different isotopic signature than crustal helium. This can help identify whether gases are coming from deeper mantle sources or from shallow crustal processes. However, Gas monitoring in Yellowstone is complicated by the fact that much of the system's gas output is diffuse. Instead of being released from a single vent, gases can seep out across broad areas through soil, springs, and fumaroles. This makes measurement challenging. Scientists use a combination of direct sampling at thermal features, soil gas surveys, and remote sensing approaches where possible. The goal is to establish baseline emission rates and detect deviations. Thermal monitoring is also essential. Yellowstone's surface heat output is enormous, and it is expressed through hot springs, geysers, fumaroles, and warm ground. Scientists measure temperatures at specific features, and also use airborne and satellite thermal imaging to detect changes in surface heat patterns. Thermal changes can indicate shifts in hydrothermal flow, new pathways opening, or changes in water supply. Again, these changes do not necessarily indicate magma movement, but they are part of the system's behavior and can be relevant to hazard assessment. One of the most important concepts in volcanic forecasting is the difference between background activity and unrest. Background activity includes frequent small earthquakes, minor deformation cycles, and stable hydrothermal discharge. Unrest refers to changes that exceed normal variability and suggest that the system's state is shifting. The challenge at Yellowstone is that the system is inherently noisy. It is always active. Therefore, scientists must define what normal looks like across multiple parameters. This requires long-term datasets and careful statistical analysis. In volcanic systems, unrest can involve patterns such as increasing earthquake magnitudes, earthquakes migrating upward toward the surface, rapid and sustained deformation, changes in gas composition indicating new magma degassing, and significant increases in heat output. If multiple indicators shift together in a coherent way, the probability of eruption increases. But even then, forecasting is probabilistic. Volcanoes do not provide perfect warning signals, and not all unrest leads to eruption. Some unrest episodes end without eruption, reflecting pressure released through hydrothermal circulation or small intrusions that do not reach the surface. Yellowstone also presents a unique challenge because hydrothermal changes can produce signals that resemble volcanic unrest. For example, if a hydrothermal system becomes pressurized, it might cause uplift and earthquake swarms. It might also change gas emissions. Yet this could still be a shallow fluid process rather than magma intrusion. This is why interpretation requires careful modeling of both magma dynamics and hydrothermal fluid behavior. In a sense, Yellowstone is not only a volcano, it is a coupled volcano-hydrothermal system, and the coupling makes signals more complex. Now let's connect monitoring to hazard communication. Yellowstone is widely discussed in public media, and misinformation is common. Claims that Yellowstone is about to erupt appear regularly, often based on normal earthquake swarms or minor uplift. This creates a communication challenge for scientists and park managers. The goal is to provide accurate information without exaggeration and without dismissing legitimate scientific interest. Yellowstone's monitoring data are publicly available through official sources, and regular updates help maintain transparency. The key message is that Yellowstone is active, but activity does not equal imminent eruption. Hazard assessment at Yellowstone includes multiple possible scenarios. The most extreme scenario is a caldera-forming supereruption, but this is extremely unlikely on human timescales. More plausible volcanic scenarios include smaller rhyolitic eruptions or basaltic eruptions in the region, which could produce lava flows and ashfall. Another realistic hazard category is hydrothermal explosions, which can occur with little warning and can be dangerous in localized areas. Earthquakes also pose hazards, especially if a larger tectonic earthquake occurs near the park, which could trigger landslides and alter hydrothermal features. From an ecological standpoint, Yellowstone's monitoring is also relevant because changes in hydrothermal activity can affect habitats. Thermal areas can influence where animals congregate in winter. For example, bison may use geothermal zones for access to forage. Elk and mule deer may also be influenced by snow conditions and thermal ground. Predators such as wolves and cougars follow prey distributions. While monitoring is primarily focused on geologic hazards, the data also contribute to understanding ecosystem dynamics in a changing environment. We should also discuss the role of scientific uncertainty. Monitoring provides data, but interpreting that data involves uncertainty because the subsurface cannot be observed directly. Scientists use models to infer processes, but models depend on assumptions and incomplete information. This does not mean the science is unreliable. It means that volcanic forecasting is inherently probabilistic. The best approach is to combine multiple data sets, update models as new information becomes available, and communicate risk in terms of likelihood and potential impact. In summary, Yellowstone is monitored through seismic networks, deformation measurements, gas emission studies, and thermal observations. Earthquake swarms are common and often related to fluid movement. Ground uplift and subsidence reflect changing pressures from magma and hydrothermal fluids. Gas emissions provide clues about deep degassing and fluid pathways. Thermal monitoring tracks the surface expression of heat flow. Volcanic forecasting relies on identifying coherent changes across these parameters rather than reacting to single signals. Yellowstone's activity is continuous, but it is not currently showing signs of imminent large eruption. The system's greatest value, scientifically, is that it provides an opportunity to study an active volcanic and hydrothermal field in real time. In the next chapter, we will return to the biological and ecological side of Yellowstone, but we will do so through the lens of geology. Specifically, we will examine how volcanic landscapes, geothermal heat, and glacial history shape habitats, migration routes, and the distribution of iconic species. Yellowstone is often described as a wilderness ecosystem, but that ecosystem is built on volcanic ground and is influenced by heat rising from below. Chapter 7. Life on volcanic ground, Yellowstone ecology, and species shaped by fire and ice. In this chapter, we are going to examine Yellowstone's ecology, but we will do it through a geological lens. Yellowstone is often presented as a wildlife spectacle, a place where visitors can see bison, wolves, bears, and elk in a setting that feels primordial. That impression is not entirely wrong. Yellowstone does contain one of the largest relatively intact temperate ecosystems in North America. However, the key scientific point is that Yellowstone's ecosystem is not separate from its geology. The distribution of habitats, the movement of animals, and even the seasonal rhythms of the park are shaped by volcanic deposits, hydrothermal heat, glaciation, and the physical structure of the Yellowstone Plateau. Let's begin with the landscape itself. Yellowstone sits at high elevation, much of it above 2,000 meters. The Yellowstone Plateau is essentially a volcanic highland, built from layers of lava flows, ash deposits, and caldera-related rocks. Over time, glaciers advanced across this region during the Pleistocene, carving valleys, leaving moraines, and shaping the drainage patterns we see today. The result is a terrain that alternates between broad open valleys, dense conifer forests, wetlands, rivers, and geothermal basins. These landscape units are the stage on which Yellowstone's biology operates. One of the most ecologically important features of Yellowstone is its valleys. Lamar Valley in the northeast and Hayden Valley in the central region are among the most famous. These valleys exist because of a combination of glacial carving, river erosion, and sediment deposition. They provide open grassland habitat that supports large herbivores, which in turn support large predators. If you want to understand Yellowstone's food web, you start in these valleys. They function as ecological centers because visibility is high, forage is abundant, and animals can move across them efficiently. The American bison, is perhaps the most iconic herbivore in Yellowstone. Yellowstone contains one of the largest free-ranging bison populations in the United States. Bison are large-bodied grazers that feed primarily on grasses and sedges. Their grazing behavior influences plant community structure, and their movement patterns shape nutrient cycling across the landscape. Bison are also strongly influenced by winter conditions. In deep snow, movement becomes energetically expensive and access to forage is limited. This is where Yellowstone's geothermal system becomes ecologically relevant. In some areas, geothermal heat keeps ground relatively snow-free or melts snow earlier in the season, exposing vegetation. Bison often use these areas as winter refuges, not because they are seeking warmth directly, but because they are seeking accessible food. Elk, Cervus canadensis, are another major herbivore species. Elk are browsers and grazers, feeding on grasses, shrubs, and tree shoots depending on season and location. Elk migrations in and around Yellowstone are influenced by elevation, snowpack, and forage availability. In winter, elk often move to lower elevations where snow is shallower. In summer, they may move into higher elevations where new plant growth is abundant. The distribution of these seasonal ranges is shaped by topography, which in turn is shaped by volcanic and glacial history. The caldera basin, surrounding mountains, and river valleys create a patchwork of habitats that elk exploit. Mule deer, Odocoleus heminus, and white-tailed deer, Odocoleus virginianus, are also present, though mule deer are more commonly associated with Yellowstone's habitats. Pronghorn, Antilocapra americana, are especially notable in the northern parts of the greater Yellowstone ecosystem. Pronghorn are adapted to open landscapes and are among the fastest land mammals in North America. Their presence is linked to open grassland and sagebrush habitats, which occur in areas shaped by glacial outwash and sedimentary soils. Again, geology is not background scenery. It is a controlling factor in habitat availability. Now let's move to the predators. The gray wolf, Canis lupus, is one of the most discussed species in Yellowstone because of its ecological role and its history of extirpation and reintroduction. Wolves were reintroduced to Yellowstone in the mid-1990s after decades of absence. Wolves primarily prey on elk, though they may also hunt deer, bison calves, and smaller mammals. Their presence influences prey behavior, movement patterns, and survival rates. Wolves also interact with other predators and scavengers, including coyotes, Canis laterans, and scavenging birds. The ecological effects of wolves are often described in terms of trophic cascades, meaning that predators can influence vegetation indirectly by reducing herbivore pressure or altering herbivore behavior. In Yellowstone, this has been discussed particularly in relation to willows and aspens along rivers and streams. Elk browsing can suppress willow growth in riparian areas, affecting habitat for beavers, Castor canadensis, and songbirds. When wolf predation reduces elk numbers or changes elk behavior, willow growth may recover in some areas. However, this story is complex, and multiple factors influence vegetation including climate, hydrology, and human land use outside the park. In a lecture setting, it is important to treat trophic cascades as a hypothesis supported by evidence in some contexts, not as a simple one-cause explanation. Grizzly bears, Ursus arctos horribilis, are another major predator and omnivore in Yellowstone. Grizzlies have large home ranges and use a wide variety of food sources. They may feed on roots, insects, berries, and carrion, and they can prey on ungulate calves. Grizzlies are strongly seasonal in their behavior. In spring, they may emerge from dens and feed on early vegetation and winter-killed carcasses. In summer, they may focus on insects and berries. In fall, they intensify feeding to build fat reserves for hibernation. The distribution is influenced by food availability, which is influenced by habitat type, which is influenced by geology and climate. American black bears, Ursus americanus, are also present and occupy similar, but often more forest-associated habitats. Cougars, puma concolor, are less frequently seen but are important predators, particularly in forested and rugged terrain. Coyotes, Canis latrans, are widespread and play roles as both predators and scavengers. Bald eagles, Haliaeetus leucocephalus, and golden eagles, Aquila chrysaetos, are also part of the ecosystem, feeding on fish, waterfowl, and carrion. Now, Yellowstone's ecology is not only large mammals. The park contains extensive aquatic systems, including the Yellowstone River, the Madison River, and Yellowstone Lake. These water systems support fish, amphibians, and aquatic invertebrates. One of the most historically important fish species in Yellowstone Lake is the Yellowstone cutthroat trout, Oncorhynchus clarki bouvieri. This species has been central to the lake's food web, supporting predators such as bears and birds. The introduction of non-native lake trout, Salvelinus namaycush, has altered this system by preying on cutthroat trout and changing fish population dynamics. This is an example of how ecological systems can be disrupted by species introductions, even in a protected area. Hydrothermal features also influence aquatic ecology. Thermal inputs can affect local water temperatures, which can alter habitat suitability for certain species. In some cases, thermal waters contain dissolved minerals and chemicals that can influence microbial communities and invertebrate life. However, most of Yellowstone's major rivers are dominated by cold water flow from snowmelt and mountain runoff, with geothermal inputs being localized rather than system-wide. One of the most important ecological forces in Yellowstone is fire. Wildfire is a natural part of the park's ecosystem, particularly in lodgepole pine forests, Pinus contorta. Lodgepole pine is adapted to fire in many areas through serotinous cones that release seeds when heated. Fires can reset forest succession, create habitat mosaics, and influence nutrient cycling. The relationship between fire and geology is significant because soil types, moisture availability, and topography influence fire behavior and post-fire recovery. Volcanic soils can vary in nutrient content and drainage, affecting how vegetation regrows after burns. Climate is another major controlling factor. Yellowstone experiences long winters, short growing seasons, and significant variability in snowpack. Climate influences migration timing, plant growth, river flow, and survival conditions for many species. In the context of Yellowstone's geothermal system, climate also influences hydrothermal behavior by affecting groundwater recharge. Snowmelt and rainfall contribute to the water supply that feeds geysers and hot springs. In drought conditions, groundwater levels may drop, potentially affecting hydrothermal discharge. This is one example of how Yellowstone's surface features are linked to broader climate patterns. Now, let's connect ecology back to the supervolcano theme. Large volcanic eruptions can drastically alter ecosystems through ashfall, habitat destruction, and climate effects. However, Yellowstone's last supereruption occurred 631,000 years ago, long before the modern ecosystems we recognize today. The landscape has been reshaped repeatedly since then by lava flows, glaciation, erosion, and sedimentation. Yellowstone's current ecology is therefore adapted to a dynamic environment, but not necessarily to supereruptions on human timescales. More relevant to modern ecology are smaller-scale disturbances such as wildfire, harsh winters, predator-prey dynamics, and human impacts at the ecosystem boundary. The geothermal system remains one of the most unique ecological influences. Thermal basins create warm microhabitats that support specialized microbial communities and can influence plant growth patterns. Thermophilic bacteria and archaea form colorful mats in hot springs, and their distribution is controlled by temperature and chemistry. These microbial ecosystems are not just scientific curiosities. They represent real biological communities with energy flows, competition, and adaptation. In some cases, they resemble conditions that may have existed on early Earth, which is why Yellowstone is studied as an analog for early life environments. Birds also respond to Yellowstone's habitats. Waterfowl use lakes and rivers. Raptors use open valleys and cliffs. Songbirds use forests and riparian vegetation. Species such as the trumpeter swan, Cygnus buccinata, can be found in wetland habitats, and their survival depends on water availability and vegetation. Beavers, Castor canadensis, influence stream structure by building dams, creating ponds that support amphibians and aquatic insects. Beaver activity can change riparian habitat in ways that affect other species, illustrating how Yellowstone's ecology is shaped by a network of interactions. To summarize, Yellowstone's ecosystem is a product of volcanic ground, glacial shaping, climate variability, fire regimes, and species interactions. Large herbivores such as bison and Cervus canadensis occupy valleys formed by geological processes. Predators such as Canis lupus and Ursus arctos horribilis shape prey populations and scavenger networks. Aquatic systems support species such as Oncorhynchus clarkii bouvieri, and ecological disruptions such as invasive fish can reshape food webs. Geothermal features create unique microhabitats for extremophile microbes and influence winter forage availability. In Yellowstone, the biological world is built directly on top of a volcanic system, and the two cannot be separated. In the next chapter, we will return more directly to volcanic hazards and future scenarios. We will discuss what kinds of eruptions Yellowstone is capable of, what the most likely future volcanic events might look like, how ashfall and pyroclastic flows would behave in the region, and how scientists evaluate risk without relying on simplistic doomsday narratives. Chapter 8. Future eruptions, realistic hazard scenarios, and what Yellowstone could do next. In this chapter, we are going to address a topic that tends to dominate public curiosity about Yellowstone, what could happen next. The phrase Yellowstone supervolcano has become a cultural idea as much as a scientific one, and it often comes with a sense of looming catastrophe. In a lecture setting, we need to approach this carefully. The goal is not to dismiss volcanic hazards, but to evaluate them in a structured way, based on what Yellowstone has done in the past, what it is doing today, and what physical conditions are required for different types of future events. The first point to establish is that Yellowstone is capable of multiple types of hazardous activity. The most extreme scenario is a caldera-forming supereruption, meaning an eruption that produces more than 1,000 cubic kilometers of erupted material. Yellowstone has produced eruptions of that scale in the past, most notably the Huckleberry Ridge event around 2.1 million years ago. However, the existence of past supereruptions does not mean such an eruption is likely in the near future. Supereruptions require very large volumes of eruptible magma, and that magma must be sufficiently molten, gas-rich, and connected. These conditions take long periods to develop. On human timescales, the more relevant hazards are smaller volcanic eruptions, hydrothermal explosions, and earthquakes. Let's organize Yellowstone's future hazards into categories. The first category is large caldera to forming eruptions. These are the rarest but highest impact events. If such an eruption occurred, it would likely involve sustained explosive activity producing widespread ashfall and massive pyroclastic density currents near the source. The collapse of the ground surface would create or modify a caldera structure. The immediate region around Yellowstone would be devastated by pyroclastic flows, which are extremely hot and fast-moving. These flows could travel tens of kilometers, potentially farther depending on topography and eruption intensity. Within that zone, survival would be unlikely. Ashfall would extend far beyond the immediate region, affecting much of the continental United States, depending on wind direction and eruption duration. The second category is smaller explosive eruptions. Yellowstone is a rhyolitic volcanic system, and rhyolitic eruptions can be explosive even when they are far smaller than supereruptions. A smaller rhyolitic eruption could produce ashfall, local pyroclastic flows, and lava domes. These eruptions might occur along ring fractures or within the caldera, where structural weaknesses exist. The impacts would be severe locally, but they would not be continent scale in the same way a supereruption would be. In terms of probability, these smaller eruptions are still uncommon, but they are more plausible than a caldera-forming event on shorter timescales. The third category is effusive eruptions, meaning eruptions dominated by lava flows rather than explosive fragmentation. Yellowstone has produced rhyolitic lava flows and domes in the post-caldera period, and basaltic volcanism also occurs in the broader region. Basaltic lava is generally less viscous and can flow more easily than rhyolite, but in Yellowstone, the dominant recent volcanic products have been rhyolitic. A future effusive eruption could produce thick rhyolite flows, which would move slowly but could bury large areas. These flows would not travel like Hawaiian lava rivers. They would advance in thick, blocky masses, forming rugged terrain. The hazard would be primarily local, but the disruption to infrastructure and ecosystems could be substantial. The fourth category is hydrothermal explosions. These are among the most realistic hazards for Yellowstone on human timescales, not because they are guaranteed, but because they can occur without new magma reaching the surface. Hydrothermal explosions occur when hot water, trapped underground, flashes into steam, expanding rapidly and fragmenting rock. The result can be an explosion crater, ejected blocks, and a localized blast zone. Hydrothermal explosions can occur in thermal basins, near geysers, or even beneath lakes. They are difficult to forecast precisely because they can be triggered by changes in pressure, sealing of conduits, or shifts in fluid pathways. In Yellowstone, evidence of past hydrothermal explosions exists in the form of craters and breccia deposits, particularly in areas near Yellowstone Lake. The fifth category is earthquakes and related hazards such as landslides. Yellowstone's region is tectonically active and it experiences frequent small earthquakes and occasional larger ones. A major tectonic earthquake, like the 1959 Hebgen Lake event, could produce landslides, ground cracking, and changes in hydrothermal activity. While earthquakes are not volcanic eruptions, they are part of Yellowstone's hazard landscape. They can also trigger secondary effects, including changes in geyser behavior, hot spring discharge, and in rare cases, hydrothermal explosions if pressure conditions are altered. Now, a key question is how scientists evaluate the likelihood of these scenarios. The answer is that volcanic hazard assessment is probabilistic and evidence-based. Scientists look at the geologic record to understand what types of events have occurred and how often. They examine the structure of the magma system using seismic imaging and other geophysical methods. They monitor real-time signals such as seismicity, deformation, gas emissions, and thermal output. By combining these datasets, they estimate probabilities for different types of activity over certain time windows. This is not prediction in the sense of a specific date. It is risk assessment in the sense of relative likelihood. For Yellowstone, the probability of a supereruption in any given year is extremely low. The probability of smaller events, such as hydrothermal explosions, is higher, though still not frequent. The probability of earthquake swarms is high because they happen regularly. This spectrum matters because it helps distinguish between dramatic but unlikely scenarios and more realistic hazards that park managers and scientists actually plan for. Let's consider what precursors might look like for a volcanic eruption at Yellowstone. In many volcanic systems, magma intrusion produces a combination of signals. Seismicity may increase, and earthquake locations may migrate upward. Ground deformation may accelerate, showing rapid uplift. Gas emissions may change, including increases in carbon dioxide flux or changes in gas ratios that indicate fresh magma degassing. Thermal output may increase, and hydrothermal features may change behavior. In Yellowstone, interpreting these signals is complicated because the hydrothermal system can produce similar patterns without magma approaching the surface. Therefore, scientists would look for sustained, multi-parameter changes that exceed baseline variability. For a hydrothermal explosion, the precursors might be subtle or absent. A localized increase in temperature, changes in water chemistry, or changes in ground stability could occur, but these may not provide clear warning. This is why hydrothermal areas are treated with caution. The hazard is not only the explosion itself, but also the unstable ground and boiling water conditions. In Yellowstone, the boardwalk systems are designed to reduce risk by keeping visitors away from fragile thermal ground. Now, let's discuss ashfall. Because ashfall is one of the most widespread hazards associated with explosive eruptions. Volcanic ash is not soft like fireplace ash. It is made of tiny, sharp fragments of volcanic glass and minerals. Ash can irritate lungs, damage machinery, contaminate water supplies, and collapse roofs if it accumulates thickly. Even moderate ashfall can disrupt transportation and agriculture. The distribution of ashfall depends heavily on wind direction and eruption height. In Yellowstone, prevailing winds often blow from west to east, meaning ash could be carried across the Great Plains and into the central United States. However, wind patterns vary, and ash distribution would need to be modeled in real time during an eruption. Pyroclastic density currents, by contrast, are primarily a near-field hazard. They would be devastating within tens of kilometers of the vent, and their path would be influenced by topography. Valleys could channel flows, while ridges might divert them. The Yellowstone Plateau's topography would play a role in determining flow paths. However, for a large caldera to forming eruption, the scale of flows could overwhelm local topographic barriers. This is one reason why caldera-forming eruptions are considered among the most catastrophic volcanic events. Lava flows, whether rhyolitic or basaltic, are generally slower hazards. Their danger lies in burial and long-term disruption rather than sudden destruction. Rhyolitic lava domes can also collapse, producing block and ash flows, which are fast-moving and dangerous. In Yellowstone, if a rhyolite dome formed, the surrounding area would likely be restricted due to the risk of collapse and explosive activity. Now, we should integrate biology again, because hazards do not occur in an ecological vacuum. A major ashfall event would affect plant photosynthesis, water quality, and animal health. Grazing animals such as bison and elk could experience respiratory irritation and reduced forage quality. Predators such as wolves and grizzly bears would be affected indirectly through prey availability and habitat disruption. Aquatic systems could be affected by ash runoff into rivers and lakes, altering turbidity and chemistry. However, ecosystems can also recover over time, and volcanic landscapes often undergo ecological succession, with pioneer species colonizing new deposits. In terms of human impacts, Yellowstone's hazards extend beyond the park boundary. The greater Yellowstone ecosystem includes surrounding communities, infrastructure, and transportation routes. A large eruption would have national and global consequences, but again, the likelihood of that scenario is extremely low in the near term. More realistic hazards, such as earthquakes and hydrothermal explosions, would primarily affect the region and park visitors. Emergency planning therefore focuses on plausible scenarios, including evacuation routes, communication systems, and visitor safety in geothermal areas. One of the most important aspects of hazard science is avoiding false certainty. It is not scientifically honest to say Yellowstone will erupt soon, and it is also not scientifically honest to say Yellowstone will never erupt again. The correct position is that Yellowstone is an active volcanic system with a range of possible future behaviors. The probability of different behaviors varies, and those probabilities are evaluated through monitoring and geologic evidence. This is the same approach used for other volcanic systems around the world. To summarize this chapter, Yellowstone's future hazards include rare but high-impact caldera-forming eruptions, less rare but still uncommon smaller rhyolitic eruptions, effusive lava flows, hydrothermal explosions, and earthquakes. The most realistic hazards on human timescales are hydrothermal explosions and earthquakes, while the most extreme hazard, a super-eruption, is extremely unlikely in the near term. Scientists evaluate these scenarios using probabilistic hazard assessment and continuous monitoring, looking for sustained multi-parameter changes that exceed baseline behavior. The goal is not to predict a date, but to understand risk and communicate it responsibly. In the next chapter, we will examine Yellowstone's deeper subsurface structure in more detail, focusing on what geophysical imaging tells us about magma storage, melt fractions, and the shape of the mantle anomaly beneath the park. This will help us connect surface observations to the hidden architecture of the system. Chapter 9. Imaging the subsurface, magma storage, and what we know about Yellowstone underground. In this chapter, we are going to focus on a fundamental challenge in volcanology and geophysics. How do we know what is happening underground when we cannot directly observe it? Yellowstone is an ideal case study because it is both scientifically important and heavily monitored. Yet even with dense instrumentation, the subsurface remains partly uncertain. The best we can do is combine multiple geophysical methods, interpret them using physical models, and revise those interpretations as new data become available. Yellowstone's underground structure is therefore not a single diagram that everyone agrees on. It is an evolving scientific picture built from evidence. Let's start with the most widely used tool for imaging volcanoes, seismic tomography. Seismic tomography works by analyzing how seismic waves travel through the Earth. When an earthquake occurs, it sends waves outward. Those waves travel at different speeds depending on the materials they pass through. In general, seismic waves travel faster through cold, solid rock and slower through hot, partially molten rock. By collecting wave arrival times at many seismometers, scientists can construct a three-dimensional model of seismic velocity beneath a region. Areas of low velocity are often interpreted as hot, partially molten or fluid-rich zones. At Yellowstone, seismic tomography has revealed a low-velocity anomaly beneath the caldera, consistent with a magma reservoir system in the upper crust. This anomaly is often described as a shallow magma body or magma storage region. However, it is critical to emphasize that low velocity does not automatically mean a giant pool of liquid magma. It can also reflect a mixture of melt, crystals, and hot rock. Most evidence suggests that Yellowstone's shallow magma system is dominated by crystal-rich mush rather than fully molten magma. This mush contains melt, but much of the volume is not eruptible at any given time. Seismic studies also suggest a deeper magma storage region in the mid-crust, beneath the shallow reservoir. This deeper zone is interpreted as a place where basaltic magma from the mantle may pond, evolve, and transfer heat upward. In a continental hotspot system like Yellowstone, basaltic magma rising from the mantle may not erupt frequently at the surface. Instead, it may stall in the crust, where it contributes heat and triggers partial melting of crustal rock. Over time, this process can generate the rhyolitic melts that dominate Yellowstone's major eruptions. In this sense, the deeper system acts as a heat engine, while the shallow system acts as a storage and processing zone. Now, let's move deeper still into the mantle. Seismic imaging has also identified a low-velocity mantle anomaly beneath Yellowstone that extends downward, consistent with a hot mantle source. This is part of the evidence supporting the hotspot interpretation. The exact geometry and depth of the mantle anomaly is still debated, but many models show a plume-like structure extending into the upper mantle. Whether this structure originates from very deep mantle or from shallower convection patterns remains an open question. What matters for Yellowstone's behavior is that the mantle beneath the region is hotter than average and capable of producing melt. Another important geophysical method is magnetotellurics, which measures the electrical conductivity of the subsurface. Conductivity is strongly influenced by temperature, melt, and fluids. Molten rock and saline fluids are more conductive than dry, solid rock. By measuring natural variations in Earth's electromagnetic field, scientists can infer conductivity patterns underground. In volcanic systems, high conductivity zones often correspond to magma bodies or hydrothermal fluid reservoirs. At Yellowstone, magnetotelluric data complement seismic data by providing additional constraints on where melt and fluids might be concentrated. Gravity studies also contribute to subsurface imaging. Gravity measurements detect variations in the density of rocks beneath the surface. A magma body or hot altered region may have a different density than surrounding rock. By mapping gravity anomalies, scientists can infer the presence of low-density regions that might correspond to partially molten zones or hydrothermally altered rock. Gravity data alone cannot uniquely identify magma, but when combined with seismic and conductivity data, it strengthens interpretations. Now, let's talk about what we mean by magma storage. In a lecture setting, it is important to avoid the simplistic idea of a magma chamber as a hollow cavity filled with liquid magma. Most modern volcanology views magma storage as a continuum. At one end, you have solid rock. At the other end, you have fully molten magma. In between, you have mush zones where crystals and melt coexist. These mush zones can be very large. They can contain significant total melt volume, but the melt may be distributed in small pockets rather than forming a connected body. Eruptions require not just melt, but melt connectivity and mobility. In Yellowstone, estimates of melt fraction in the shallow reservoir vary depending on the method and model, but many interpretations suggest melt fractions that are substantial enough to sustain hydrothermal heat flow, but not necessarily high enough to be immediately eruptible at a super-eruption scale. This is a key point for hazard communication. The presence of melt does not mean Yellowstone is about to erupt. It means Yellowstone is an active volcanic system with a persistent heat source. We should also discuss the relationship between magma and hydrothermal fluids. Yellowstone's hydrothermal system is enormous, and it is driven by heat from below. The hydrothermal system likely occupies the upper few kilometers of the crust, where water can circulate through fractures. This system is not separate from the magma system. It sits above it, extracts heat from it, and in some cases may interact with magmatic gases. However, the hydrothermal system can also produce signals that mimic magmatic unrest, such as ground deformation and earthquake swarms. Understanding the boundary between hydrothermal and magmatic processes is one of the central challenges in Yellowstone research. One way scientists approach this is by analyzing the depth distribution of earthquakes. Magma movement often produces earthquakes at certain depths, while hydrothermal fluid movement tends to produce shallow earthquakes. In Yellowstone, many earthquakes occur at shallow to mid-crustal depths, consistent with both tectonic faulting and hydrothermal activity. Some deeper earthquakes may reflect magmatic processes, but depth alone is not enough. Scientists also examine the type of seismic waves produced, looking for signatures of fluid involvement, such as long-period events or tremor. Yellowstone does not typically produce the same kind of sustained volcanic tremor seen at some active erupting volcanoes, which is consistent with the fact that it is not currently erupting. Deformation patterns also help infer subsurface structure. For example, if uplift is centered over a broad area and can be modeled as pressure increase at a certain depth, that provides constraints on whether pressurization is occurring. In Yellowstone, deformation often involves uplift of the caldera floor, sometimes centered near the resurgent domes such as Sour Creek and Mallard Lake. Modeling these patterns suggests pressurization at depths of several kilometers, consistent with either magmatic intrusion or hydrothermal fluid accumulation. Again, distinguishing between these requires integrating additional data. Gas geochemistry provides another window into the subsurface. Carbon dioxide emissions can indicate deep degassing, because carbon dioxide can escape from magma at depth and travel upward through fractures. Helium isotope ratios can help identify mantle contributions. In Yellowstone, some gas emissions show mantle-derived signatures, supporting the idea that deep magmatic processes contribute to surface degassing. However, gas pathways can be complex, and gases may be modified by interaction with groundwater and rock. Gas data therefore provide important clues, but they must be interpreted in context. Now, let's consider how magma might be distributed beneath Yellowstone in a conceptual model. A commonly discussed model includes a shallow rhyolitic reservoir beneath the caldera, a deeper basaltic reservoir in the mid-crust, and a mantle source feeding basalt upward. Basalt intrusions provide heat and volatiles, driving crustal melting and rhyolite generation. Rhyolitic melt accumulates in the shallow crust, and over long periods it can produce eruptions. The hydrothermal system sits above these reservoirs, circulating water and releasing heat to the surface. This model is consistent with many observations, but the details remain uncertain. The exact sizes, shapes, melt fractions, and connectivity of these reservoirs are active research topics. We should also address the spatial scale of Yellowstone's subsurface system. Yellowstone's volcanic field extends beyond the park boundaries. The greater Yellowstone region contains volcanic deposits, faults, and geothermal areas that reflect a broad zone of crustal heating and deformation. The hotspot track across the Snake River Plain indicates that the system is part of a long-lived mantle process. Therefore, Yellowstone's subsurface architecture cannot be fully understood by focusing only on the park. It is part of a regional system that includes tectonic extension, mantle upwelling, and crustal evolution. Now, let's return briefly to biology, because subsurface imaging might seem disconnected from ecology, but the connection is real. The distribution of geothermal features at the surface is controlled by subsurface permeability and heat flow, Those geothermal features influence habitats, winter forage access, and microbial ecosystems. The thermophilic microbial mats in hot springs are, in a sense, biological expressions of subsurface temperature gradients. Even large mammals like bison respond to geothermal areas in winter because snowmelt exposes vegetation. The underground structure therefore shapes not only volcanic hazard, but also the daily functioning of the ecosystem. Another important aspect of subsurface structure is the role of faults. Faults provide pathways for fluid flow and can influence where geothermal features emerge. Faults also concentrate stress and can produce earthquakes. In Yellowstone, fault networks interact with the caldera ring fractures and with regional basin and range faults. This structural complexity contributes to the distribution of hydrothermal basins and to the patterns of seismicity. It also means that changes in stress or fluid pressure can propagate through the system in complicated ways. In terms of future research, improving subsurface imaging at Yellowstone involves increasing seismic station density, integrating different geophysical methods, and refining models of melt distribution. One major challenge is that geophysical signals can be non-unique. A low seismic velocity zone might reflect melt, but it might also reflect hot fluids or altered rock. A high conductivity zone might reflect melt, but it might also reflect saline hydrothermal fluids. This is why multiple methods are necessary. The best interpretations come from convergence among datasets. To summarize this chapter, Yellowstone's subsurface structure is inferred through seismic tomography, magnetotellurics, gravity studies, deformation modeling, and gas geochemistry. These methods reveal a complex magma storage system with shallow and deeper components, fed by a mantle heat source. The magma is best described as a mush zone, with varying melt fraction rather than a single giant chamber of liquid magma. The hydrothermal system sits above the magma system and interacts with it, complicating the interpretation of surface signals. Faults and fractures control fluid pathways and contribute to seismicity. The underground architecture is therefore complex, dynamic, and still being refined through ongoing research. In the next chapter, we will conclude the lecture series by integrating everything we have discussed into a coherent framework. We will summarize Yellowstone as a coupled hotspot volcano hydrothermal ecosystem system, revisit what is scientifically solid versus uncertain, and end with a grounded understanding of what Yellowstone is and why it matters. Chapter 10. Yellowstone as a living system, what we know, what we don't, and why it matters. In this final chapter, we are going to bring the Yellowstone system together into a single integrated framework. Up to this point, we've examined Yellowstone from multiple angles: hotspot dynamics, magma chemistry, caldera formation, hydrothermal physics, eruption history, monitoring methods, ecology, and hazard scenarios. The reason we have taken that approach is that Yellowstone cannot be understood as a single subject. It is not only a volcano, and it is not only a park. Yellowstone is a coupled system in which deep earth processes shape surface landscapes, and surface landscapes shape ecosystems. The scientific value of Yellowstone lies in that coupling, because it allows us to observe how geology and biology coexist on top of an active volcanic heat source. Let's start with what we know with high confidence. We know that Yellowstone is underlain by an anomalous mantle heat source. The clearest evidence is the hotspot track extending across the Snake River Plain, which shows a progression of volcanic centers that match the motion of the North American plate. This is not speculative. The age progression of volcanic deposits is well documented, and the spatial pattern is consistent with a relatively stationary heat source beneath a moving plate. We also know that Yellowstone's heat flow is unusually high, and that it sustains one of the largest hydrothermal systems on Earth. The existence of thousands of hot springs and geysers requires a persistent heat source and extensive groundwater circulation. We also know that Yellowstone has produced extremely large eruptions in the past. The Huckleberry Ridge Tuff, Mesa Falls Tuff, and Lava Creek Tuff represent three major caldera-forming eruptions over the past 2.1 million years. These eruptions produced vast ignimbrite deposits and reshaped the region. The geologic evidence for these events is strong, including widespread ash layers, welded tuffs, and caldera structures. The timing of these eruptions is constrained through geochronology, and the deposits can be mapped and analyzed in detail. In other words, Yellowstone's history as a large silicic volcanic system is not a matter of debate. It is a documented part of North American geology. We also know that Yellowstone's current caldera formed around 631,000 years ago, and that the caldera has been modified by post-caldera volcanism, resurgence, faulting, and hydrothermal alteration. The caldera's resurgent domes, such as Sour Creek and Mallard Lake, show that the caldera floor has been uplifted over time by subsurface processes. We know that the ground surface continues to rise and fall on decadal timescales, and we can measure those changes precisely using GPS and satellite radar. We know that Yellowstone experiences frequent earthquakes, including swarms, and that many of these are likely related to fluid movement and stress changes in the crust. We also know that Yellowstone's hydrothermal system is chemically diverse and physically dynamic. We can observe geyser cycles, hot spring chemistry, fumarole emissions, and mineral deposition directly. We know that geysers require a particular plumbing geometry that allows pressure to build and release cyclically. We know that acidic thermal areas are often associated with volcanic gases and sulfuric acid formation, while alkaline thermal areas can deposit silica sinter. We also know that Yellowstone's thermal environments support extremophile microbes, and that these microbial communities have contributed to scientific breakthroughs, including the discovery of heat-stable enzymes. On the ecological side, we know that Yellowstone supports a large and relatively intact food web, including large herbivores such as bison, and elk, Cervus canadensis, as well as predators such as wolves, Canis lupus, and bears, including the grizzly bear, Ursus arctos horribilis. We know that these species interact through predation, scavenging, competition, and habitat use. We also know that Yellowstone's ecology is shaped by fire, climate, and seasonal migration. These processes operate on timescales that are visible within decades, and they can be studied directly through field observation and long-term monitoring. Now, we should also be clear about what we do not know with the same level of certainty. One major uncertainty is the exact geometry and depth extent of the mantle anomaly beneath Yellowstone. Seismic imaging shows a low-velocity region consistent with hot mantle, but whether it is a narrow plume rising from very deep mantle or a broader upwelling shaped by upper mantle convection is still debated. This is a reminder that even when evidence supports a general mechanism, details remain unresolved. Another uncertainty is the precise structure of Yellowstone's magma system in terms of melt fraction, connectivity, and eruptibility. We can infer the presence of partially molten zones through seismic and electrical conductivity data, but we cannot directly measure melt percentage everywhere underground. We can model it, and we can constrain it, but it remains an interpretation. The concept of a magma mush zone is widely accepted, but the exact distribution of melt pockets and how they might connect under changing conditions is an active research topic. We also cannot predict exactly when Yellowstone will erupt again, or what form that eruption will take. We can say with confidence that Yellowstone will erupt again on geologic timescales because it has done so repeatedly and remains active, but the timescales relevant to human life are much shorter than the timescales of major volcanic events. The last caldera, deforming eruption, occurred 631,000 years ago. More recent eruptions have been smaller rhyolitic lava flows, and even those occurred tens of thousands of years ago. In terms of probability, the most likely events in the near term are not super eruptions, but smaller-scale hazards such as hydrothermal explosions and earthquakes. Even then, exact timing cannot be predicted with certainty. This leads us to an important scientific principle. Monitoring is not about predicting an exact date, but about detecting changes in system state. Yellowstone is monitored because it is active and complex, and because it is valuable to understand baseline behavior. Seismic networks record earthquakes, GPS and INSAR detect formation, gas sampling tracks emissions, and thermal imaging monitors heat output. These datasets provide a continuous record. If Yellowstone were to enter a state of significant volcanic unrest, it would likely produce a multi-parameter signal that differs from its normal patterns. That is what monitoring is designed to detect. However, Yellowstone's coupled magma hydrothermal system complicates forecasting. Hydrothermal pressure changes can produce uplift and earthquake swarms that resemble magmatic signals. Earthquakes can alter geyser behavior without any change in magma. Fluid migration can produce seismic swarms. Therefore, interpretation requires integration. A single swarm does not equal eruption. A single uplift episode does not equal eruption. Scientists look for sustained, coherent changes across multiple indicators. This is a central lesson in modern volcanology. Context and convergence matter more than any single measurement. Now, let's step back and ask why Yellowstone matters scientifically. One reason is that it provides a rare opportunity to study a continental hotspot system in detail. Most hotspots are oceanic, like Hawaii, where magma rises through thin crust and produces basaltic volcanoes. Yellowstone is different because it sits beneath thick continental crust. This creates evolved rhyolitic magmas, caldera-forming eruptions, and extensive hydrothermal circulation. Studying Yellowstone helps scientists understand how continental crust interacts with mantle-derived magma, how large silicic reservoirs form, and how caldera systems evolve over hundreds of thousands of years. Yellowstone also matters because it is one of the best places on Earth to study hydrothermal physics at scale. The density of geysers and hot springs provides a natural laboratory for understanding fluid circulation, boiling dynamics, mineral precipitation, and geothermal energy transfer. The chemical diversity of Yellowstone's thermal waters allows scientists to study water-rock interaction, gas chemistry, and the formation of hydrothermal minerals. These studies are relevant not only to volcanology, but also to geothermal energy research, mineral exploration, and environmental chemistry. The microbial ecosystems of Yellowstone are another reason it matters. Extremophiles in Yellowstone have reshaped our understanding of the limits of life. They have also provided tools for biotechnology. The idea that life can thrive in near boiling, acidic, or chemically extreme environments has implications for understanding early Earth and for evaluating the possibility of life on other planets and moons. In that sense, Yellowstone is not only a park, it is a place where the boundaries of biology have been tested and expanded. Yellowstone also matters as a model for hazard communication. Few geological systems have been so deeply embedded in public imagination. The phrase Yellowstone supervolcano often triggers fear, fascination, or misinformation. Scientists and park managers must communicate about Yellowstone in a way that is accurate, calm, and grounded in evidence. This includes acknowledging the real hazard potential, while also emphasizing the rarity of extreme events and the importance of monitoring. Yellowstone is therefore a case study in how science interacts with public perception. Now, let's integrate the ecological perspective one final time. Yellowstone's wildlife, including bison, Cervus canadensis, Canis lupus, and Ursus arctos horribilis, exists on terrain shaped by volcanic eruptions and glacial cycles. Valleys formed by ice and sediment provide grazing habitat. Forests regrow after fires. Rivers cut through volcanic deposits. Geothermal heat influences winter habitat use and creates microhabitats for microbes. In Yellowstone, ecology is layered on top of geology, and the two are interdependent. This is one reason the greater Yellowstone ecosystem is so scientifically valuable. It is not only a wildlife preserve, it is an ecosystem operating on top of an active geological engine. So, what should a listener take away from this lecture series? The first takeaway is that Yellowstone is real science, not mythology. It is a hotspot-driven volcanic system with a documented history of large eruptions and ongoing geothermal activity. The second takeaway is that Yellowstone is complex. Its magma system is not a single chamber, and its surface signals are influenced by both magma and hydrothermal fluids. The third takeaway is that hazard assessment must be probabilistic and multi-parameter. Extreme events are possible but rare. More common activity includes earthquakes, hydrothermal changes, and ground deformation. The fourth takeaway is that Yellowstone is valuable beyond hazards. It is a natural laboratory for studying Earth processes, hydrothermal chemistry, and microbial life. Finally, Yellowstone matters because it reminds us that Earth is not static. Landscapes that appear permanent are, on geologic timescales, temporary. Valleys shift, rivers change course, ecosystems migrate, and heat rises from below. Yellowstone is one of the clearest places on Earth where you can see that reality at the surface. The geysers erupt on a schedule measured in minutes. The ground rises and falls on a schedule measured in years. The caldera forms on a schedule measured in hundreds of thousands of years, and the hotspot track forms on a schedule measured in millions of years. Yellowstone contains all of those timescales at once, layered together in a single place. That is why Yellowstone is not just a park. It is a system, and it is still active.